Lung disease classification and quantification with explainable AI is our project title. In this project, we are developing an application for early detection of lung diseases such as COVID and pneumonia using X-ray images. Lung diseases is one of the deadliest category of disease for mankind, and many European countries are trying to detect it at early stage using X-ray images. But the lack of availability of radiologists is a challenge, and in the country like us where testing kits of COVID are not available, the application could be a very reliable solution. We have managed a decent size of database with the help of our mentor Dr. Manoj Gaur. We are having 6,500 X-ray images of chest, out of which 2,755 images are for no findings normal images category, 3,153 images of pneumonia and 645 images of COVID category. As we are having less images of COVID, so we are using GAN for generating new COVID images using augmentation. We have divided this total data set in two parts of 80 and 20, 80 for training part and 20 for testing purpose.
Hello everyone. In our project we have used a CNN model. We know that there are many architectures available for CNN like LeNet, GoogleNet, ResNet, VGG and so on. Among this we have chosen 3 different architectures to deploy our model, to develop our model for finding whether the person has pneumonia, COVID or whether he is normal or not. Let me explain briefly about these architectures. So first comes ResNet. The main base element of ResNet is residual block. As we go deeper into the network with increasing number of layers, the computation becomes more and more complex. And most importantly, we have to do batch normalization after each convolutional layer, and no dropout is used here. So next comes DenseNet. DenseNet consists of dense blocks. Within these blocks, the layers are densely connected together. So each layer gets input from its previous layer or to fish maps. So this extreme use of residuals makes this network more powerful. Finally, we used VGGNet. It is an architecture which consists of a pair of convolutional layer and pooling layer, and at the end fully connected layer. Right now it has models with 16 to 19 layers. It uses very small filter with more depth. We have imported all these architecture in our project using its pre-trained model. Yes, we have used DenseNet 121, ResNet 50 and VGG 19 in our project. Since we got very less accuracy for DenseNet and ResNet, we preferred using VGGNet. Yeah, for DenseNet and ResNet we got accuracy less than 80%, but for VGGNet we got accuracy more than 80% for 3 classes.
So, as we are getting good accuracy in VGG19 model as compared to other ResNet and DenseNet model, we decided to go with VGG19 model for our image classification, where we train our model for around 100 epochs for 3 classes, which are COVID, normal and pneumonia, where we are getting accuracy around 85 to 90%. In order to increase the accuracy of our model, we try to train it for around 500 epochs, but due to heavy RAM uses, Google Colab every time terminates our program and we are unable to further train it. To overcome this issue, we have trained 3 different models with 2 classes each, which are COVID-19 normal, pneumonia normal and COVID-19 pneumonia. By doing this approach, in each classes we are getting more than 90% accuracy. We split the dataset into 80-20 ratio for training and testing. For normal and COVID model, we train it for 80 epochs with 32 batch size and getting result of 93 accuracy. For normal and pneumonia model, we train it for 50 epochs with batch size 32 and getting accuracy around 91%. And for COVID and pneumonia model, we train it for 50 epochs and 32 batch size and getting accuracy of 93%.
Now that we have implemented transfer learning on a dataset, the next thing we try to implement is semi-supervised GAN on a dataset. Semi-supervised GAN is an extension of GAN architecture which involves simultaneous learning of supervised discriminator, unsupervised discriminator and the generated model. The discriminator thus predicts k plus 1 classes, where k is the number of classes in the prediction problem and the other class is for the fake class. The pre-processing of the image is similar to that of the transfer learning methods. In the normalization, we normalize the image such that the pixel values fall between -1 and 1. And also, as the dataset is fully labeled, we unlabel some of the images by using the function which we define called label mask. After splitting the dataset into test and train, we define the generator and discriminator models. The generator model follows a standard implementation as that of the DCGAN paper. It involves taking a random vector set and reshaping it into 4D tensor and then feed it to a sequence of transpose convolutions, batch normalizations and Lie-Creelio functions. Coming to the discriminator, it's a multi-class classifier, but it also follows a similar architecture as a DCGAN paper. We just pass it into a stack of convolutions, batch normalizations and Rayleigh functions. Now coming to the loss function of the semi-supervised GAN. It contains of two losses, the discriminator loss and the generator loss. The discriminator loss is again of two parts, the unsupervised discriminator loss and the supervised discriminator loss. In the unsupervised discriminator loss, it's just the loss between the real training images and the fake generator images. In supervised discriminator loss, it's just a multi-class classification problem in which we use softmax cross entropy function. Now coming to the generator loss, we use future matching for the generator loss. Future matching is a concept of penalizing the mean absolute error between the average value of some set of the futures on the training data and the average values of that set of the futures on the generated samples. After defining all the functions and running the code, we are getting a cross-validation accuracy of the test data about 90% and the cross-validation loss of the generator and discriminator less than 1.
First question arises is why we are using explainable AI. We are using explainable AI so the result can be understood by the humans easily. It gains trust of human on AI. It explains why the AI arrives at a specific decision. It contrasts with the black box learning in machine learning, where even the designers don't know why the algorithms comes to a specific decision. Basically, explainable AI is an implementation of social rights to explanation. We are using LIME algorithm of explainable AI here to explain our results. LIME is basically model agnostic. That means it can be applied to any machine learning algorithm. The technique attempts at understanding model by analyzing the input of data sample and understanding how the prediction changes. The result of classifier recognizing whether the X-ray have COVID-19 or pneumonia or basically nothing, and the information regarding the part of X-ray based on which the model made the decision. This is all about the explainable AI for our project. So we have developed a deep learning model with explainable AI for multi-class image classification. We have also implemented this classification using semi-supervised GAN with deep learning algorithms. A new horizon has been provided to medical imaging application and new possibilities have been created for smart medical analysis. Deep learning has been provided to be helpful in solving those problems which were previously thought to be unsolved by machine learning algorithms. Thank you, and that's all from our side.